In this presentation, we want to display how to assess the cooling or heating demand of a building linked to ventilation. And for doing that, we will use a tool that is the Psychrometric chart, and we are going to introduce it and to display how to use it. Ventilation is taking place when outside air and inside air are exchanged. Because of that, a corresponding heat or cooling load is risen. As well, the flow and the energy balance associated to it must be provided by means of the air handling units. The flow and the energy can be partly recovered. We cannot see here the criteria for sizing the ventilation itself. That depends upon many constraints: machines requirement, hygienic reasons, norms, etc. We limit our study to evaluate how much energy is exchanged by the ventilation and which performance is requested by the climatization units. For doing that, we rely on a graphic calculation tool that is the psychrometric diagram. That diagram represents the transformations of air, and air is actually not dry but humid. Therefore, we speak about a mixture air-moisture. At a given ambient pressure, the thermodynamic state of such a mixture is defined by two independent parameters, and the state can be represented in a two-dimensional diagram. The psychrometric diagram uses as horizontal axis the dry bulb temperature and as vertical axis the absolute humidity. A state is represented by a point in the diagram, and to find it, it is enough to choose any couple of variables among dry bulb temperature, wet bulb temperature, absolute humidity, relative humidity, and enthalpy. A transformation is a line connecting two states. To get the energy exchanged in kilowatt, it is enough to find the delta enthalpy in kilojoule per kilogram and multiply it by the dry air mass flow in kilogram per second. The dry mass air flow is not given by the diagram. It must be known up front. For a given transformation, the dry air mass stays constant. They are special transformations which are mostly used in the applications and easy to represent in the diagram. Heating or cooling are horizontal lines since they have constant x, where x is the absolute humidity. Humidification by water has constant enthalpy. Humidification by steam has constant temperature instead. Condensation is taking place along the saturation line, always towards lower temperature. Another use of the diagram is to find the final state after mixing two air flows. Actually, this is not a proper transformation since the air mass is changing. Let's see now how to calculate the energy associated to ventilation by using a formula. Actually, the heat load is always the product between the mass flow and the delta enthalpy. If the specific humidity is not changing during the transformation, that means no condensation and no humidification, then we can use the formula displayed where m dot is the mass flow of the dry air, Cp is the specific heat of the air, T1 and T2 the outside and inside temperatures, X the specific humidity, and R the latent heat of the water. For a quick calculation, we can consider Cp and R constant. The values are given in red. Instead of using formulas, it is quicker and often more precise to use the psychrometric diagram. Let's see here an example where we consider to heat a space. Airflow is given 10,000 cubic meter per hour. Moreover, temperature of outside and inside are known, respectively 0 and 20 degrees. The absolute humidity of outside is also given, 0.0035,
corresponding to a relative humidity of 90%. We assume no humidification. Also, X is not changing during the transformation. The chart says we need 70.7 kW, and same result we could have found with the formula. Important to convert volumetric flow into mass flow by means of the air density, that is also depending upon temperature. Since the temperature is changing, which temperature to take for density? Actually, it depends where the ventilator is placed. If the ventilator is after the exchanger, then the inside temperature must be used. Last but not least, the psychrometric chart is sensitive to the ambient pressure. The ambient pressure depends upon the altitude. The proper setting must be done in advance and stays valid for all the following calculations at same location. If the transformation is including a change in humidity, the previous formula cannot be used. We need to calculate the enthalpy H separately, once for the inside and one for the outside air, and then get the difference. If you reuse the example of the previous slide, taking the inside air at 50% RH, that corresponds to X 0.075, the corresponding heat load will be 106 kW. In such a case, a humidification section after the exchanger is needed, as displayed in the drawing. Let's consider now a cooling example. Question is, are the formulas the same? Theoretically, yes, but if together with the cooling also dehumidification is needed, then we face a technological problem. Should we need to keep 25 degrees at 60 RH inside, while outside the temperature is 37 degrees and RH 40%, the required transformation is the one in blue between P2 and P1. This process we need to split into two, one dehumidification at constant temperature and one cooling at constant X. For the dehumidification, we need a special absorption wheel that is normally not used because bulky and expensive. The theoretical cooling demand is 69.2 kW. The normal way to proceed is different and makes the dehumidification per condensation. We need to split the process in 3 stages, actually 4, but the fourth is free of charge. First, the cooling up to saturation at constant X, the blue line. Then the condensation along the saturation line where both temperature and humidity drop, the lilac line. Finally, a heating process at constant X, the red line. This heating is needed to achieve the wanted temperature in the room. Actually, we do not need to heat up to the final temperature because part of the heating we get free of charge due to the heat losses across walls, windows, roofs, and also because of the thermal loads of the machinery inside of the building. In the example, we assume that those losses are 15 kW, so that we stop the heating at about 20 degrees. The corresponding cooling demand is the sum of the two steps P2 PP1 and PP1 P3, also nearly 98 kW. On top, there is a heating step of about 12 kW that we need to give through the air handling unit as well. In such a case, the air handling unit must have 2 coils in a row, one for cooling and one for heating. Is there any possibility to reduce the cooling load? Yes, if we change the equipment. Rather than air supply device and exhaust fan separated, we need a combined device for supply and exhaust with a heat exchanger in between, so that we can partly recover the cold contained in the exhaust air. We keep same temperature data of the example before, and we consider a further transformation up front, that is the heat exchange. We represent this step in green in the diagram. We consider a simplified model for that, and we assume the heat exchange like an air mix, where the temperature is the same of the mix, and the humidity the same of the inlet air. That because there is a physical separation between inlet and outlet flows. We will see this detail in the next slide. The remaining steps are the same. The point P2S, that is representing the entry air after the exchanger, is found by moving the point PP5 vertically to match same x as P2. The delta T between P2 and P2S is gained by the exchanger. The rest stays as per the previous process. The result is a saving of about 20% of cooling load.
Thank you very much for your attendance. See you next time. Bye bye.